Welcome. In this video, we are going to discuss about phase delay and group delay of LTI systems. So, what is phase delay? We all know what is an LTI system. Basically, it is a system which can be represented or characterized by an impulse response or a frequency response. And let's see what an LTI system does to a real sinusoidal signal. It just has some gain term and it has some phase delay term, a delay term. This is the phase shift, okay, and this is the gain. Now, look at this term, the phase shift term. This phase shift term, it is a shift in phase, but okay, how do I relate it to how many samples it is shifting my cosine by? How many samples in the time domain is that shift? So simple way, you just take out omega naught as common and n plus some term which will have the same units as samples. So we call this term as tau p, which is a delay term. That's why we have a negative sign here. And what is this tau p? This term is called as the phase delay. So tau p as a function of omega is negative sign theta omega upon omega. Theta omega is the phase response of an LTI system at a frequency omega, and if I divide it by omega, okay, so the theta omega is the phase shift, right? How much my phase is changing. But theta omega by omega with a negative sign, this is how many samples my signal is delayed by. So my signal is shifted or delayed by that many samples. That's the only thing. So this is the concept of phase delay. It's the number of samples my signal is shifted by because of an LTI system. That's it. Now let's look at another term, group delay. Because in real world we may not get pure sinusoids. So it is interesting to see other kinds of signals also. We start with one example where my signal is a popular signal, popularly used in communications. It is a modulated, amplitude modulated cosine signal or sinusoid. So how do I write it? It is some a times cos omega mn times cos omega cn, where omega c is the carrier frequency and it is much larger than omega m, which is my modulation frequency. Omega c is very large, as you can see in the graph here, that this very rapidly changing signal is my omega c, and this very gently, very slowly changing signal is my omega m, and these two are getting multiplied. So now I want to see what is the LTI system. How will the LTI system modify this signal? So what is my yn? So I don't know how to compute the effect of LTI system on multiplication of cosines, but I know this is an LTI system, which means a linear system, so I know how it responds to individual sinusoids. So, but we have read trigonometry and we can convert product of cos into a sum of cosines. How do we do that? So it's a upon 2 and omega c minus omega m times n, right, cos of this term, plus omega c plus omega m times n, right? You add and subtract. So this is our signal, and now I know how will my LTI system respond to it. But let's take a moment to see how this signal looks like in the frequency domain. Okay, I have my x e to the power j omega. I'm plotting it with respect to omega, and this is my omega c, which is here, and omega m is very very small as compared to omega c, and my signal, there are peaks at omega c minus omega m. Okay, this gap is omega m, and then omega c plus omega m. This gap is omega m. So these are my two peaks represented by this signal, right? So, and now let's see how will my LTI system respond to this input. So the output will be very simple. Y of n is equal to, I have my a upon 2, and what is this? This is the gain for the first frequency, omega c minus omega m, the lower frequency, and cos of omega c minus omega n times n, plus the phase shift in the lower frequency, plus the gain for the higher frequency, the upper frequency, and times the cos of omega c plus omega m, the basically our base higher frequency, plus some phase shift in the higher frequency. This is it, that's it. So now I know how to compute the response to two individual sinusoids. And let us call this frequency as the theta L, the phase response for the lower frequency, and theta U as the phase response to the upper frequency. And now I have to understand the structure of this signal. It looks complicated, but we can use some real world approximations. One approximation is we let omega c minus omega m, so my magnitude or the gain at omega c minus omega m, this and this are almost same. You know, we have assumed that omega m is small, and if my LTI system, the magnitude gain is continuous, and we can assume that omega m is, if omega m is very small, then these are approximately same. Okay, so these are approximately same. Now we can take them out, and what remains is just the cosine terms. Okay, I can just, this is a constant, and let us, this is not of interest for our discussion, so let us put it as equal to 1. Even if it is some other value, doesn't matter. Now let's look at what is my y of n. My y of n is, now I am trying to convert my sum of cosines into product of cosines, because I want to see how the signal will look like. So I want to plot my y of n now. So my y of n simply becomes, you know how to convert sum of cosines into product of cosines. You have this plus this divided by 2, right, into cos of this minus this divided by 2. Right. So that's what we saw. Let's write it down here again. My y of n is simply a cos, yeah, this is the thing. So now my y of n is simply omega c n plus this thing, omega mn plus this thing. Okay, now can I, like, this may not make much sense to me, but can we make some more approximations? So let us assume that my theta omega c, which means let this be locally linear, right? It means my omega m is very close, and we can assume that in that small neighborhood my theta is locally linear, is linear in that neighborhood basically. So what does that lead to? So if this happens, then my omega c plus any small frequency, which we know actually is omega m, but let's call it as delta omega, small frequency, we can assume that this is equal to theta omega c plus d theta upon d omega delta omega. What is this called? This is called Taylor's expansion, and we have assumed that my theta omega c is locally linear, and we can ignore the higher order terms, right? Note this point that we are ignoring the higher order terms on the premise that theta omega c is locally linear, which means if my delta omega is very small, then we can use this approximation. Now, so therefore, let us compute, I want to compute my y, so let us see what is theta u then. Theta u is, originally it was omega c plus omega m, the phase response at omega c plus omega m. So this is equal to theta of omega c, using this approximation, plus d theta upon d omega at omega c times the delta omega, which is omega m. Now, very simple. Now, what will be my theta L? So, the same thing, but just that instead of plus, I will have a negative sign. So, a negative sign here and a negative sign here. That's it. So, now let's plug these values into my y of n and see how y of n looks like. Can we plot? So, let's take it as y of n is equal to a. So, I write theta u plus theta L as, like, these two are getting added. You remember there was a plus and negative sign, so those get cancelled and we just get theta omega c. So this is what we finally get. Theta omega omega c n plus theta omega c. That's it. And this term, you see, when you subtract the two, then theta omega c gets cancelled and only omega m times the derivative remains, the linear expansion term. So this is what is my y of n finally. This looks much better actually. We can correlate it with my x of n, right? X of n also had some carrier wave and some modulation wave, and this also has a carrier wave plus some phase shift and modulation wave plus some phase shift. Let us now apply the same technique to convert my phase shift into phase delay, which is in units of samples. So this is what I get. Let me rush through this part. Yeah, the same thing, right? Then this was the phase shift, and I use a negative sign to signify that this thing is called delay. This is delay in time, delay in number of samples. So now this part is my tau p as a function of omega c, right? This part. And what about this part? This part is called tau g as a function of omega c, which is simply the derivative of omega, derivative of theta omega at omega c. So these are two things. Earlier, when this was not present, we only had a phase delay term. But now if there is a modulation frequency present, when the modulation frequency is very small, we also get a group delay term. So basically, my carrier wave gets shifted by these many samples, and my modulation wave gets shifted by these many samples. So if you are working on communications, then you are interested in your modulation signal. And notice one thing here. Notice one thing here, that even the group delay, you don't calculate the derivative at omega m, but you calculate the derivative of at omega c only, because omega m is very small, and we just assume that it's a linear approximation, right? So, but I have to calculate both these things at the right place. Let me just give me a second. Let me clarify. Like, let's say if my theta omega c looks something like this, some function, and if I have here, I'm sorry, I should have drawn it in another way. Let me just erase this part. Let me draw it again. So let's say if I have my group delay thing, something like this, right? So let us say I look at this point. This point is my omega c. Then what is my phase delay? My phase delay is basically this term, theta omega c divided by this. So basically the height is omega c, right? Sorry, the base is omega c and the height is theta omega c. I should not have written omega c here. It is just omega. Now this point will be, or this height will be theta omega c, right? And whereas this base is omega c, so this tan theta is omega c upon theta omega c upon omega c. Whereas if you look at the group delay term, use another pen. So if you want to compute the group delay here, it's the slope of this line, the slope of the tangent. So the slope of this angle is the tan of this angle, basically, which is the derivative of this point. This is my group delay, and whereas this gives me my, this will give me my phase delay, right? So I hope this point is clear. So okay, let's summarize the whole thing. So what we have obtained is phase delay is the delay in the carrier, right? I have a carrier frequency, how much the carrier frequency gets shifted, how many samples my carrier frequencies gets delayed by. And the group delay is the delay in the modulation or in the envelope. How many samples does my modulation get delayed by? And as we have discussed that we are assuming theta omega c is linear in that small locality. That locality depends on omega m, right? And if we assume that my phase response is linear in that small locality around omega c, then we get a linear group delay. But if it is not linear, then we will have higher order terms in the expansion and we get phase distortion. There will be double derivative, triple derivative, and then they're all getting multiplied with omega c. So there will be, or omega m, so there will be phase distortion. Yeah, thank you very much. So these were the concepts of phase delay and group delay.